Network layer addressing. In this video, we are going to see about network layer addressing. At the network layer, we need to uniquely identify each device on the internet to allow global communication between all devices. Internet address. The identifier used in the network layer of the Internet model to identify each device connected to the Internet is called the Internet address or IP address. An IP address in the current version of the protocol is a 32-bit binary address that uniquely and universally defines the connection of a host or a router to the Internet. Classful addressing. In the mid-1990s, a new architecture called classless addressing was introduced, which will eventually supersede the original architecture. However, most of the Internet is still using classful addressing and the migration is slow. In classful addressing, the IP address space is divided into 5 classes A, B, C, D, and E. Each class occupies some part of the whole address space. Unicast, multicast, and reserved addresses. Addresses in classes A, B, and C are for unicast communication from one source to one destination. A host needs to have at least one unicast address to be able to send or receive packets. Addresses in Class D are for multicast communication from one source to a group of destinations. If a host belongs to a group or groups, it may have one or more multicast addresses. A multicast address can be used only as a destination address, but never as a source address. Addresses in Class E are reserved. The original idea was to use them for special purposes. They have been used only in a few cases. Network address. The network address is an address that defines the network itself. It cannot be assigned to a host. Subnetting. When an organization is given a block of class A, B, or C addresses, the first address in the block defines the network address. This address is used by routers outside the organization to route the packets destined for the network. The outside world, when it comes to routing, recognizes the network, not the individual hosts on the network. A portion of a 32-bit address indicates the network, that is net ID, and a portion indicates the host, that is host ID on the network. This means that there is a sense of hierarchy in IP addressing. To reach a host on the Internet, we must first reach the network by using the first portion of the address, that is net ID. Then we must reach the host itself by using the second portion, host ID. In other words, IP addresses are designed with 2 levels of hierarchy. However, often an organization needs to assemble the hosts into groups. The network needs to be divided into several subnetworks, that is subnets. Subnet mask. The number of ones in a subnet mask is more than the number of ones in the corresponding default mask. In other words, in a subnet mask, we change some of the leftmost zeros in the default mask to make a subnet mask. Supernetting. Although Class A and B addresses are almost depleted, Class C addresses are still available. However, the size of a Class C block with a maximum number of 256 addresses may not satisfy the needs of an organization. Even a mid-size organization may need more addresses. In supernetting, an organization can combine several Class C blocks to create a larger range of addresses. Introduction to routing concepts. In this video, we are going to see about Introduction to routing concepts. A router has two functions as follows. Forwarding function. It is a function that allows selection of the appropriate route based on IP header information and sends packets through this route. Filtering function. It is a function that allows dumping of invalid packets for a specific network instead of forwarding. Forwarding function. The most important processing in forwarding is to determine the route. In general, routing refers to the processing used for determining the next hop, that is, IP address of next router. Here, we consider that the processing for sending packets to the host in the same network is also performed as an integral part of routing. Routing in the same network may be termed as local routing. The routing is simple if the destination address of the host is in the same subnet. However, if it is not in the same subnet, the packet must be sent to the boundary router first. The boundary router references the routing table to determine the next hop. Routing table varies in configuration depending on the routing method used. The routing table possessed by a router includes combination of destination address and a next hop that corresponds to that address. This table lists destination addresses for each local network and not for each destination host. This table also includes as the next hop the address of next router to which the packet must be transferred. If no hops are included, this means that the destination network is directly connected to the router. When router A receives a packet, it tracks this table to perform routing. For example, if the packets addressed to the host of the network 138.25.40.0, then router A sends the packets to router C, that is 138.25.30.1. Router C has a similar routing table so that it can perform routing. Filtering function. In this video, we are going to see about filtering function. The second function available with the router is that it can filter packets to determine whether they can pass through. For example, consider that there are two networks connected via router. Now we impose the following conditions. Hosts A and C cannot communicate using UDP packets. Host B cannot use FTP for communication with host D. Host D cannot communicate with host A. Host D can communicate with host B only using telnet. In this case, the network administrator sets the router as given below. Exclusion list. Source host is equal to A. Destination host is equal to C, protocol is equal to UDP. Source host is C, destination host is A, protocol is UDP. Source host is B, destination host is D, port is FTP. Source host is D, destination host is A. Inclusion list. Source host is C, destination host is B, protocol is Telnet. Routing methods: static routing, dynamic routing. In this video, we are going to see about routing methods, that is static routing, dynamic routing. Routing requires a host or a router to have a routing table. When a host has a packet to send or when a router has received a packet to be forwarded, it looks at this table to find the route to the final destination. However, this simple solution is impossible today in an internetwork such as the internet because the number of entries in the routing table makes table lookups inefficient. Several techniques can make the size of the routing table manageable and handle issues such as security. We will discuss these methods here. Static routing table. A static routing table contains information entered manually. The administrator enters the route for each destination into the table. When this type of table is created, it cannot update automatically when there is a change in the internet. The table must be manually altered by the administrator. A static routing table can be used in a small internet that does not change very often or in an experimental internet for troubleshooting. It is not good strategy to use a static routing table in a big internet such as the internet. Dynamic routing table. A dynamic routing table is updated periodically using one of the dynamic routing protocols such as RIP, OSPF, or BGP. Whenever there is a change in the internet, such as a shutdown of a router or breaking of a link, the dynamic routing protocols update all the tables in the routers and eventually in the host. The routers in a big internet such as the internet need to be updated dynamically for efficient delivery of the IP packets. Distributed routing. In this video, we are going to see about distributed routing. Distributed routing. For routing in a network having two or more routers, routing tables are used to determine the destination to which a packet is to be forwarded. If two or more routes are available, the route that requires the least possible cost, that is link cost, should be selected so that the packet can be sent to the destination more quickly and more reliably. Cost can be generally considered as the number of routers via which the packet is to be sent. If changes are made to this network configuration, there are two methods to update the contents of routing tables, which will be described next. Link cost. Link cost can be defined in a variety of ways. Routing algorithm, on the other hand, functions regardless of the intention with which link cost has been specified. If there is no specific intention, the cost for a single link is usually set at 1. In this case, only the number of hops is taken into consideration. If response time is important, the route with the minimum delay will be the best choice. For example, if there are two routes, one in which packets are sent over a single 9600 bps line and the other in which packets are sent over 200 mbps FDDI lines, the latter route is better because there is less delay, although there are more hops. To ensure that rule calculations are performed in this way, the cost should be smaller for a link with smaller delay, and the cost should be larger for a link with larger delay. Also, the user may wish to minimize the communication cost. Therefore, least line is better from the point of view of cost. Load distribution methods. If there are two or more routes to reach the same destination and the same cost, throughput can improve because load is distributed. In addition, delay can be reduced because traffic per route is reduced. Therefore, it is useful to be able to perform multipath routing when two or more routes are available at the same cost. Multipath routing can be achieved in both distance vector type and link state type. If there are two or more routes to reach the same destination at the same cost, one of the following methods is applicable to determine which of these routes is to be used and how to select this route. Round robin method sequentially selects each of the routes. Random selection method. With the round robin method, there will be a difference in traffic between routes because packet lengths are different. To solve this problem, random numbers and so on are used to randomly select the route. Mixed method. Mixture of the above two methods with also route availability taken into consideration and selects a route that is comparatively less busy. The mixed method seems superior to the other methods in that the availability of routes are taken into consideration. In the mixed method, however, the router must check in real time whether routes are available. Hierarchical routing. In this video, we are going to see about hierarchical routing. At a certain point, the network may grow to the point where it is no longer feasible for every router to have an entry for other router. So the routing will have to be done hierarchically. When this routing is used, the routers are divided into regions. It contains all the details about how to route packets to destinations within its own region. Sometimes, two-level hierarchy may be insufficient. It is necessary to group the regions into clusters, the clusters into zones, and zones into groups, and so on. Hierarchical table for 1A. Full table for 1A. For router 1A has 17 entries in full routing table. When hierarchical routing is used, only 7 entries valid for 1A. There are entries for local routers, but all other regions have been condensed into a single router. Hierarchical routing increases the saving the table space. Distance vector protocol. In this video, we are going to see about distance vector protocol. Distance vector routing protocols are based on one of two algorithms known as Bellman-Ford and Ford-Fulkerson. In distance vector routing, Each router maintains a routing table indexed by and containing one entry for each router in the subnet. It is the combination of distance and a direction. The distance is metric and the direction is the next hop to take in the path to the destination. Router learns the information from a neighbor and then pass it on to the another neighbor. Drawback of distance vector routing is split horizon and count to infinity problem. Distance vector routing protocols are Routing Information Protocol, that is RIP, DEC's DNA Phase 4, Cisco's IGRP, Routing Table Maintenance Protocol, that is RTMP. RIP is common protocol for distance vector routing. Distance vector algorithms adapt to changes in network topology gradually as the information on the changes percolates through the network. Distance vector algorithm is iterative, asynchronous, and distributed. Algorithm is iterative because this process continues on until no more information is exchanged between neighbors. It is asynchronous in that it does not require all of the nodes 40 operate in local step with each other. It is distributed in that each node receives some information from one or more of its directly attached neighbors, performs a calculation, and may then distributes the result of its calculation back to its neighbors. Let cost A, E be the cost of the cheapest route from node A to node E. Count to infinity problem. An imagined network and denotes the distances from router A to every other router. The illustration shows that link AB is broken. Router B observed it, but in his routing table he sees that router C has a route to A with 2 hops. The problem is that router B does not know that C has router B as successor in his routing table on the route to A. That occurs followed count to infinity problem. B actualizes his routing table and takes a route to A over router C. We can see the new distances to A. In C's routing, the route to A contains router B as next hop router. So, if B has increased its cost to A, C is forced to do so. Router C increases its cost to A about B plus 1 is equal to 4. Now, we see the consequence of the distributed Bellman-Ford protocol. Because router B takes the path over C to A, he reactualizes his routing table and so on. Link State Protocol. In this video, we are going to see about Link State Protocol. Link State Protocols of IP are classless protocols. In Link Routing Protocol, each router floods information about the state of the links that connect it to its neighbors. Link state protocols use an arbitrary metric. Functions of route in link state routing is as follows. Router discover its neighbors and learn their network addresses. Measure the delay or cost to each of its neighbors. Construct a packet telling all it has just learned. send this packet to all other routers. Compute the shortest path to every other router. OSPF protocol is used in a link state algorithm. Link state routing protocols are as follows. Open shortest path first, that is OSPF. Network Link Services Protocol, that is NLSP. Apple's AURP. ISO's Intermediate System, that is ISIS. Link state routing protocols from adjacencies with neighbors. Benefit of this is as follows. Relationship with neighbors allow them to unicast or multicast their updates instead. Open shortest path first, that is OSPF. In this video, we are going to see about open shortest path first, that is OSPF. OSPF is a link state routing protocol. OSPF is based on the distributed map concept. All nodes have a copy of the network map which is regularly updated. Each node contains a routing directory database. This database contains information about the router's interfaces that are operable as well as status information about adjacent routers. This information is periodically broadcast to all routers in the same domain. The OSPF computes the shortest path to the other routers. OSPF protocol is now widely used as the interior router protocol in TCP/IP networks. OSPF computes a route through the internet that incurs the least cost based on a user configurable metric of cost. The user can configure the cost to express a function of delay, data rate, or other factors. OSPF is able to equalize loads over multiple equal cost paths. OSPF is classified as an internal gateway protocol, that is IGP, because it supports routing within one autonomous system only. The exchange of routing information between autonomous systems is the responsibility of another protocol, an external gateway protocol, that is EGP. OSPF can support on our many networks. Following is the features of the OSPF. OSPF supports multiple circuit load balancing because it can store multiple routes to a destination. OSPF can converge very quickly to network topology change. OSPF support multiple metrics. OSPF is not susceptible to routing loops. OSPF support for variable length subnetting by including the subnet mask in the routing message. OSPF introduces a two-level hierarchy for improving scalability. It allows an AS to be partitioned into several groups called areas that are interconnected by a central backbone area. An area is identified by a 32-bit number known as the area ID. The backbone area is identified with area ID 193.0.0.0. The information from other area is summarized by area border router that have connections to multiple areas. OSPF uses 4 types of routers. An internal router is a router with all its links connected to the networks within the same area. An area border router is a router that has its links connected to more than one area. A backbone router is a router that has its links connected to the backbone. An autonomous system boundary router, that is ASBR, is a router that has its links connected to another autonomous system. Routers R1, R2, and R7 are internal routers. Routers R3, R6, R8 are area border routers. Routers R3, R4, R5, R6, R8 are backbone routers. Router R4 is an ASBR. The Hello protocol allows neighbors to be discovered automatically. Two routers are said to be neighbors if they have an interface to a common network. The OSPF protocol runs directly over IP using IP protocol 89. The header format for OSPF is shown. OSPF header analysis is given below. Version. This field specifies the protocol version. Type. This field indicates messages as one of the following type. Database description. Link status. Link status update. Link status acknowledgement. Packet length. This field specifies the length of OSPF packet in bytes, including the OSPF header. Router ID. It identifies the sending router. This field is typically set to the IP address of one of its interfaces. Area ID. This field identifies the area this packet belongs to, that is transmitted. Checksum. The checksum field is used to detect errors in the packet. The checksum is performed on the entire packet. Authentication type. It identifies the authentication type that is used. Authentication. This field includes a value from the authentication type. The OSPF operation consists of the following stages. OSPF send the hello messages for discovering the neighbors, and designated routers are elected in multi-access networks. Adjacencies are established and link state databases are synchronized. Link state advertisements are exchanged by adjacent routers to allow topological databases to be maintained and to advertise inter-area and inter-AS routes. The routers use the information in the database to generate routing tables. OSPF advantages. Low traffic overhead. OSPF is economical of network bandwidth on links between routers. Larger network metrics. This allows a network planner the freedom to assign costs for each path around the network to give fine control over routing paths. OSPF disadvantages. Memory overhead. OSPF uses a link state database to keep track of all routers and networks within each attached area. With a complex topology, this database can be much larger than the corresponding routing pool and may limit the maximum size of an area. Configuration. OSPF can be complex to configure. Introduction to Internet Protocol, that is IP. In this video, we are going to see about Introduction to Internet Protocol, that is IP. The Internet Protocol IP is the primary network protocol by which data is sent from one computer to another on the Internet. Each computer, known as a host, on the Internet has at least one IP address that uniquely identifies it from all other computers on the Internet. The functions of Internet Protocol include defining the Internet addressing schemes, moving data between the network access layer and host-to-host transport layer, performing fragmentation and reassembly of datagrams, routing datagrams to remote hosts. There are currently two versions in Internet Protocol, IPv4 and IPv6. Overview of Internet Protocol version 4. Internet Protocol version 4, that is IPv4, is the fourth version of the IP and a widely used protocol in data communication over different kinds of networks. IPv4 is a connection-less protocol used in packet-switched layer networks such as Ethernet. It provides a logical connection between network devices by providing identification for each device. Internet Protocol version 4 standard that features IP addresses 4 bytes, that is 32 bits in length. IPv4 uses 4 1-byte decimal numbers separated by a dot, that is 192.168.1.1. There are many ways to configure IPv4 with all kinds of devices, including manual and automatic configurations depending on the network type. Overview of Internet Protocol version 6. The Internet Protocol version 6 IPv6 is more advanced and has better features compared to IPv4. It has the capability to provide an infinite number of addresses. IPv6 is replacing IPv4 to accommodate a growing number of networks worldwide and help solve the IP address problems. The newer Internet Protocol version 6 IPv6 standard features addresses 16 bytes, that is 128 bits in length. IPv6 uses hexadecimal numbers that are separated by colons, that is FE80: D4A8: 6435: D2D8: D9F3B11. IPv4, IPv6. IPv4 address are 32 bits in length. IPv6 address are 128 bits in length. IPv4 address are binary numbers represented in decimals. IPv6 addresses are binary numbers represented in hexadecimals. IPsec supports is only optional. Inbuilt IPsec supports. Fragmentation is done by sender and forwarding routers. Fragmentation is done only by sender. No packets flow identification. Packet flow identification is available within the IPv6 header using the flow label field. Checksum field is available in IPv4 header. No checksum field is in IPv6 header. Options fields are available in IPv4 header. No options fields but IPv6 extension headers are available. Address Resolution Protocol ARP is available to map IPv4 address to MAC address. Address Resolution Protocol ARP is replaced with a function of Neighbor Discovery Protocol NDP. Internet Group Management Protocol (IGMP) is used to manage multicast group membership. IGMP is replaced with Multicast Listener Discovery (MLD) messages. Broadcast messages are available. Broadcast messages are not available. Instead, a link local scope all nodes multicast IPv6 address, that is FF02 is equal to 1, is used for broadcast similar functionality. Manual configuration static of IPv4 addresses or DHCP dynamic configuration is required to configure IPv4 addresses. Auto configuration of addresses is available. Addressing. In this video, we are going to see about addressing. As with any other network layer protocol, the IP addressing scheme is integral to the process of routing IP datagrams through an internetwork. Each IP address has specific components and follows a basic format. These IP addresses can be subdivided and used to create addresses for subnetworks. Each host on a TCP IP network is assigned a unique 32-bit logical address that is divided into two main parts: network number, host number. Network number. The network number identifies a network and must be assigned by the Internet Network Information Center (INTERNIC) if the network is to be a part of the Internet. An Internet Service Provider (ISP) can obtain blocks of network addresses from the INTERNIC and can itself assign address space as necessary. Host number. The host number identifies a host on a network and is assigned by the local network administrator. IP address format. The 32-bit IP address is grouped 8 bits at a time, separated by dots and represented in decimal format known as dotted decimal notation. Each bit in the octet has a binary weight about 128, 64, 32, 16, 8, 4, 2, 1. The minimum value for an octet is 0 and the maximum value for an octet is 255. An IP address consists of 32 bits. IP address classes. IP addressing supports 5 different address classes: A, B, C, D, and E. Only classes A, B, and C are available for commercial use. The leftmost, that is high order bits, indicates the network class. In an IP address of 172.31.1.2, for example, the first octet is 172 because 172 falls between 128 and 191. 172.31.1.2 is a Class B address. Routing. In this video, we are going to see about routing. Routing is the act of moving information across an internetwork from a source to a destination. Along the way, at least one intermediate node typically is encountered. Routing is often contrasted with bridging, which might seem to accomplish precisely the same thing to the casual observer. The primary difference between the two is that bridging occurs at layer 2, that is the link layer of the OSI reference model, whereas routing occurs at layer 3, that is the network layer. This distinction provides routing and bridging with different information to use in the process of moving information from source to destination, so the two functions accomplish their task in different ways. Routing involves two basic activities: determining optimal routing paths, transporting information groups, typically called packets, through an internetwork. In the context of the routing process, the latter of these is referred to as packet switching. Although packet switching is relatively straightforward, path determination can be very complex. Switching algorithms is relatively simple. It is the same for most routing protocols. In most cases, a host determines that it must send a packet to another host. Having acquired a router's address by some means, the source host sends a packet addressed specifically to a router's physical, that is, Media Access Control MAC layer address, this time with a protocol that is network layer address of the destination host. As it examines the packet's destination protocol address, the router determines that it either knows or does not know how to forward the packet to the next hop. If the router does not know how to forward the packet, it typically drops the packet. If the router knows how to forward the packet, however, it changes the destination physical address to that of the next hop and transmits the packet. If the three routers are part of the internet, it will only work this way when both hosts have valid public IP addresses assigned to them. Internet Control Message Protocol (ICMP). In this video, we are going to see about Internet Control Message Protocol (ICMP). The ICMP is an extension to the Internet Protocol which is used to communicate between a gateway and a source host to manage errors and generate control messages. The Internet Protocol IP is not designed to be absolutely reliable. The purpose of control messages ICMP is to provide feedback about problems in the communication environment, not to make IP reliable. There are still no guarantees that a datagram will be delivered or a control message will be returned. Some datagrams may still be undelivered without any reports of their loss. The higher-level protocols that use TCP/IP must implement their own reliability procedures if reliable communication is required. IP is an unreliable protocol that has no mechanisms for error checking or error control. ICMP was designed to compensate for this deficiency. However, ICMP does not correct errors, simply reports them. ICMP uses the source IP address to send the error message to the source of the datagram. ICMP messages consist of error reporting messages and query messages. The error reporting messages report problems that a router or a destination host may encounter when it processes an IP packet. In addition to error reporting, ICMP can diagnose some network problems through the query messages. The query messages in pairs give a host or a network manager specific information from a router or another host. Types. There are two classes of ICMP messages. Error messages have a type from 0 to 127. Informational messages have a type from 128 to 255. Code varies according to the message type. Checksum used to detect data corruption in the ICMP message and parts of the IPv4 header. Body of message varies according to the message type. Address Resolution Protocol (ARP). In this video, we are going to see about Address Resolution Protocol (ARP). ARP is a protocol used for mapping an IP address to a computer connected to the local network LAN. Since each computer has a unique physical address called a MAC address, ARP converts the IP address to the MAC address. This ensures that each computer has a unique network identity. ARP message format. Following fields are the Address Resolution Protocol (ARP) message format. Hardware type. Hardware type field in the Address Resolution Protocol (ARP) message specifies the type of hardware used for the local network transmitting the Address Resolution Protocol (ARP) message. Ethernet is the common hardware type and the value for Ethernet is 1. The size of this field is 2 bytes. Protocol type. Each protocol is assigned a number used in this field. IPv4 is 2048, that is 0x0800 in hexa. Hardware address length. Hardware address length in the Address Resolution Protocol, that is ARP message, is length in bytes of a hardware MAC address. Ethernet MAC addresses are 6 bytes long. Protocol address length. Length in bytes of a logical address, that is IPv4 address. IPv4 addresses are 4 bytes long. Opcode. Opcode field in the Address Resolution Protocol ARP message specifies the nature of the ARP message, 1 for ARP request and 2 for ARP reply. Sender hardware address. Layer 2, that is MAC address, address of the device sending the message. Sender protocol address. The protocol address, that is IPv4 address of the device sending the message. Target hardware address. Layer 2, that is MAC address of the intended receiver. This field is ignored in requests. Target protocol address. The protocol address, IPv4 address of the intended receiver. Working of Address Resolution Protocol ARP. Step 1. When a source device wants to communicate with another device, source device checks its Address Resolution Protocol ARP cache to find it already has resolved MAC address of the destination device. If it is there, it will use that MAC address for communication. To view the Local Address Resolution Protocol ARP cache, open Command Prompt and type ARP-A without double quotes using Windows operating systems. Step 2. If ARP resolution is not there in local cache, the source machine will generate an Address Resolution Protocol ARP request message. It puts its own data link layer address as the sender hardware address and its own IPv4 address as the sender protocol address. The target hardware address will be left blank since the machine is trying to find that. Step 3. The source broadcasts the Address Resolution Protocol ARP request message to the local network. Step 4. The message is received by each device on the LAN since it is a broadcast. Each device compare the target protocol address, that is IPv4 address of the machine to which the source is trying to communicate, with its own protocol address, that is IPv4 address. Step 5. When the targeted device checks the target protocol address, it will find a match and will generate an Address Resolution Protocol ARP reply message. It takes the sender hardware address and the sender protocol address fields from the Address Resolution Protocol ARP request message and uses these values for the targeted hardware address and targeted protocol address of the reply message. Step 6. The destination device will then update its Address Resolution Protocol ARP cache since it needs to contact the sender machine soon. Step 7. Destination device send the Address Resolution Protocol ARP reply message, and it will not be a broadcast but a unicast. Step 8. The source machine will process the Address Resolution Protocol ARP reply from destination. It stores the sender hardware address as the layer 2 address of the destination. Step 9. The source machine will update its Address Resolution Protocol ARP cache with the sender hardware address and sender protocol address it received from the Address Resolution Protocol ARP reply message. Proxy ARP. Proxy ARP is a method that allows hosts on different LANs to successfully transmit packets across an internetworking environment. Dynamic Host Control Protocol, that is DHCP. In this video, we are going to see about Dynamic Host Control Protocol, that is DHCP. DHCP dynamically assigns IP addresses to hosts. That is, DHCP allows addresses to be leased for some period of time. Once the lease expires, the server is free to return that address to its pool. DHCP relies on the existence of a DHCP server that is responsible for providing configuration information to hosts. Since the goal of DHCP is to minimize the amount of manual configuration required for a host to function, it would rather defeat the purpose if each host had to be configured with the address of a DHCP server. Thus, the first problem faced by DHCP is that of server discovery. To contact a DHCP server, a newly booted or attached host sends a DHCP discover message to a special IP address 255.255.255.255, that is an IP broadcast address. This means it will be received by all hosts and routers on that network. In the simplest case, one of these nodes is the DHCP server for the network. The server would then reply to the host that generated that discovery message, that is, all the other nodes would ignore it. However, it is not really desirable to require one DHCP server on every network. because this still creates a potentially large number of servers that need to be correctly and consistently configured. Thus, DHCP uses the concept of a relay agent. There is at least one relay agent on each network, and it is configured with just one piece of information, the IP address of the DHCP server. When a relay agent receives a DHCP discover message, it unicasts it to the DHCP server and awaits a response, which it will then send back to the requesting client. The format of a DHCP message. The message is actually sent using a protocol called UDP, that is, the User Datagram Protocol that runs over IP. DHCP is derived from an earlier protocol called BOOTP, and some of the packet fields are thus not strictly relevant to host configuration. When trying to obtain configuration information, the client puts its hardware address, for example its Ethernet address, in the channel address field. The DHCP server replies by filling in the YI address, that is your IP address field, and sending it to the client. Other information such as the default router to be used by this client can be included in the options field. In the case where DHCP dynamically assigns IP addresses to hosts, it is clear that hosts cannot keep addresses indefinitely, as this would eventually cause the server to exhaust its address pool. At the same time, a host cannot be depended upon to give back its address, since it might have crashed, been unplugged from the network, or been turned off. Thus, DHCP allows addresses to be leased for some period of time. Once the lease expires, the server is free to return that address to its pool. A host with a leased address clearly needs to renew the lease periodically if in fact it is still connected to the network and functioning correctly. Note that DHCP may also introduce some more complexity into network management, since it makes the binding between physical hosts and IP addresses much more dynamic. Network Address Translation (NAT). In this video, we are going to see about Network Address Translation (NAT). NAT, defined in RFC 1631, allows a host that does not have a valid registered IP address to communicate with other hosts through the internet. The host might be using private addresses or addresses assigned to another organization. In either case, NAT allows these addresses that are not internet ready to continue to be used and still allows communication with hosts across the internet. NAT achieves its goal by using a valid registered IP address to represent the private address to the rest of the internet. The NAT function changes the private IP addresses to publicly registered IP addresses inside each IP packet. The router performing NAT changes the packet source IP address when leaving the private organization and the destination address in each packet forwarded back into the private network. Network 200. The NAT feature configured in the router labeled NAT performs the translation. Overloading NAT with port address translation (PAT). some networks need to have most, if not all, IP hosts reach the internet. If that network uses private IP addresses, the NAT router needs a very large set of registered IP addresses. With static NAT, for each private IP host that needs internet access, user need a publicly registered IP address. Overloading allows NAT to scale to support many clients with only a few public IP addresses. The top part of the figure shows a network with 3 different hosts connecting to a web server using TCP. The bottom half of the figure shows the same network layer in the day with 3 TCP connections from the same client. All 6 connections connect to the server IP address 170.1.1.1 and www port 80, the well-known port for web services. In each case, the server differentiates between the various connections because their combined IP address and port numbers are unique. NAT takes advantage of the fact that the server really doesn't care if it has one connection each to 3 different hosts or 3 connections to a single host IP address. So, to support lots of inside private IP addresses with only a few global, publicly registered IP addresses, NAT overload uses Port Address Translation PAT. Instead of just translating the IP address, it also translates the port number. NAT overload can use more than 65,000 port numbers, allowing it to scale well without needing very many registered IP addresses in many cases, like in small office or home networks, needing only one. Taking the device called a router by most users apart, it contains different components. Exhaustion of IPv4 addresses gave birth to a next generation Internet Protocol version 6. IPv6 addresses its nodes with 128-bit wide address, providing plenty of address space for future to be used on entire planet or beyond. IPv6 has introduced any cast addressing but has removed the concept of broadcasting. IPv6 enables devices to self-acquire an IPv6 address and communicate within that subnet. This auto-configuration removes the dependability of dynamic host configuration protocol, that is DHCP servers. This way, even if the DHCP server on that subnet is down, the hosts can communicate with each other. IPv6 provides new feature of IPv6 mobility. Mobile IPv6 equipped machines can roam around without the need of changing their IP addresses. IPv6 is still in transition phase and is expected to replace IPv4 completely in coming years. At present, there are few networks which are running on IPv6. There are some transition mechanisms available for IPv6 enabled networks to speak and roam around different networks easily on IPv4. They are dual stack implementation, tunneling, NATPT. Mobile IP. In this video, we are going to see about mobile IP. IP addressing system makes working easier than mobile IP. Every IP address contains three fields: the class, the network number, and host number. For example, xxx.yyyy.zzz.www. In this, xxx.yyyy gives the class of IP and network number. The zzz.www is the host number. Routers all over the world have routing tables telling which line to use to get to network xxx.yyyy. Whenever a packet comes in within a destination IP address of the form xxx.yyyy.zzz.www, it goes out on that line. If new IP address is configured to machine corresponding to its new location is unattractive because large number of users, programs and database would have to be informed of the change. Another approach is to have the routers use complete IP address for routing instead of just the class and network. For this, each router requires millions of table entries. Following are some rules for using mobile IP. Each mobile host must be able to use its home IP address anywhere. Software changes to the fixed host were not permitted. Changes to the router software and tables were not permitted. No overhead should be incurred when a mobile host is at home. In mobile IP, every site that wants to allow its users to roam has to create a home agent and create foreign agent for visitors. When a packet arrives at the user's home local area network, it comes in at some router attached to the LAN. The router then tries to locate the host in the usual way by broadcasting an ARP packet asking. The home agent responds to query by giving its own Ethernet address. The router then sends packet for that address to the home agent. At the time the mobile host moves, the router probably has its Ethernet address cached. To replace that Ethernet address with a home agent is a trick called gratuitous ARP is used. Cryptographic authentication protocol are used for security. Process-to-process delivery in transport layer. In this video, we are going to see about process-to-process delivery in transport layer. The data link layer is responsible for delivery of frames between two neighboring nodes over a link. This is called a node-to-node delivery. The network layer is responsible for delivery of datagrams between two hosts. This is called host-to-host delivery. Real communication takes place between two processes, application programs. The transport layer is responsible for process-to-process delivery. Client-server paradigm. Although there are several ways to achieve process-to-process communication, the most common one is through the client-server paradigm. A process on the local host called a client needs services from a process usually on the remote host called a server. For communication, we must define the following: local host, local process, remote host, remote process. Multiplexing and demultiplexing. The addressing mechanism allows multiplexing and demultiplexing by the transport layer. Multiplexing. At the sender side, there may be several processes that need to send packets. However, there is only one transport layer protocol at any time. There is a many-to-one relationship and requires multiplexing. Demultiplexing. At the receiver side, the relationship is one-to-many and requires demultiplexing. The transport layer receives datagrams from the network layer. Connectionless versus connection-oriented service. A transport layer protocol can either be connectionless or connection-oriented. Connectionless service. In a connectionless service, the packets are sent from one party to another with no need for connection establishment or connection release. Connection-oriented service. In a connection-oriented service, a connection is first established between the sender and the receiver. Data are transferred. At the end, the connection is released. We will see shortly that TCP and SCTP are connection-oriented protocols. Reliable versus unreliable. In the Internet, there are three common different transport layer protocols as we have already mentioned. UDP is connectionless and unreliable. TCP and SCTP are connection-oriented and reliable. To understand that, error control at the data link layer does not guarantee error control at the transport layer. Three protocols. The original TCP/IP protocol suite specifies two protocols for the transport layer, UDP and TCP. We first focus on UDP, the simpler of the two, before discussing TCP. A new transport layer protocol, SCTP, has been designed. The position User Datagram Protocol. In this video, we are going to see about User Datagram Protocol. UDP is another transport protocol in the TCP/IP suite. User Datagram Protocol is an Open Systems Interconnection (OSI) transport layer protocol for client-server network applications. The service provided by UDP is an unreliable service that provides no guarantees for delivery and no protection from duplication. The simplicity of UDP reduces the overhead from using the protocol, and the services may be adequate in many cases. UDP is widely used in video conferencing and real-time computer games. The protocol permits individual packets to be dropped and UDP packets to be received in a different order than that in which they were sent, allowing for better performance. UDP header format. An UDP datagram header contains 4 fields of 2 bytes each. Source port number, destination port number, datagram size, checksum. Source port number. UDP 16-bit packets from a client use the source port as a service access point (SAP) to indicate the session on the local client that originated the packet. UDP packets from a server carry the server SAP in this field. Destination port number. UDP packets from a client use this as a service access point (SAP) to indicate the service required from the remote server. Datagram size. The length field specifies the length of the whole packet in octets, including header and data portions. The shortest possible packet can be 8 octets long. Checksum. An optional 16-bit checksum computed over the entire UDP datagram plus a special pseudo-header of fields. Transmission Control Protocol (TCP). In this video, we are going to see about Transmission Control Protocol (TCP). The second transport layer is protocols TCP. TCP, Transmission Control Protocol, is a protocol that works with the Internet Protocol IP to send packets of data between computers over the Internet. TCP establishes a full duplex virtual connection between two endpoints. Each endpoint is defined by an IP address and a TCP port number. The operation of TCP is implemented as a finite state mission. TCP IP protocols are modeled in 4 layers. TCP operation. The primary purpose of the TCP is to provide reliable, secureable logical circuit or connection service between pairs of processes. To provide this service, Internet Communication System requires facilities in the following areas: basic data transfer, reliability, flow control, multiplexing, connections. Basic data transfer. TCP is able to both transmit and receive data streams simultaneously, even though this is opposite to the basic concept of data transmission in many underlying network technologies. The TCP is able to transfer a continuous stream of data in each direction between its users by packaging some number of data into segments for transmission through the Internet system. In general, the TCPs decide when to block and forward data at their own convenience. The data unit transmitted from TCP layer is referred to as a segment. The size of the segments and the timing at which they are sent is generally left to the TCP module. TCP applications request that the data is pushed by instructing the TCP module to deliver all data up to that point without maximum transmission unit (MTU). Reliability. TCP assigns a sequence number to each byte transmitted and expects a positive acknowledgement ACK from the receiving TCP. If the ACK is not received within the timeout interval, the data is then retransmitted. The receiving TCP uses the sequence numbers to rearrange the segments when they arrive out of order and to eliminate duplicate segments. TCP provides reliable communication through a positive acknowledgement system. Flow control. TCP provides a means for the receiver to govern the amount of data sent by the sender. This is achieved by returning a window with every ACK indicating a range of acceptable sequence numbers beyond the last segment successfully received. The window indicates an allowed number of octets that the sender may transmit before receiving further permission. Multiplexing. TCP is able to provide a connection-oriented environment for many simultaneous processes within a single host. TCP uses a set of ports which, when concatenated with the IP address of the host, providing a socket that uniquely identifies an application process anywhere within the Internet. Connections. The reliability and flow control mechanisms described above require that TCPs initialize and maintain certain status information for each data stream. The combination of this information, including sockets, sequence numbers, and window sizes, is called a connection. Each connection is uniquely specified by a pair of sockets identifying its two sides. When two processes wish to communicate, their TCP must first establish a connection, initialize status information on both sides. When the communication is complete, the connection is terminated or closed to free the resources for other users. TCP header. The TCP segment comprises of a header and a variable length data area that ultimately carries application data. TCP header at minimum is 20 bytes long and maximum 60 bytes. Source port 16 bits identifies source port of the application process on the sending device. Destination port 16 bits identifies a destination port of the application process on the receiving device. Sequence number 32 bits. Sequence number of data bytes of a segment in a session. Acknowledgement number 32 bits. When ACK flag is set, this number contains the next sequence number of the data byte expect and works as acknowledgement of the previous data received. Data offset 4 bits. This field contains two meanings. First, it tells the size of TCP header 32-bit words. Secondly, it indicates the offset of data in current packet in the whole TCP segment. Reserved 3 bits. Reserved for future use and all are set 0 by default. Flags 1 bit each. NS nonce some bit is used by explicit congestion notification signaling process. CWR. When a host receives packet with ECE bit set, it sets congestion windows reduced to acknowledge that ECE received. ECE has two meanings. If SYN bit is clear to 0, then ECE means that the packet has its CE, that is congestion experience, bit set. If SYN bit is set to 1, ECE means that the device is ECT capable. URG indicates that urgent pointer field has significant data and should be processed. ACK indicates that acknowledgement field has significance. If ACK is clear to 0, it indicates that packet does not contain any acknowledgement. PSH, when set, it is a request to the receiving station to push data as soon as it comes to the receiving application without buffering it. RST, reset flag, has many features. It is used to refuse an incoming connection. It is used to reject a segment. It is used to restart a connection. SEN. This flag is used to set up a connection between hosts. FIN. This flag is used to release a connection and no more data is exchanged thereafter. Because packets with SYN and FIN flags have sequence numbers, they are processed in correct order. TCP client-server model. TCP is a peer-to-peer connection-oriented protocol. There are no master or subordinate relationships. The applications, however, typically use a client-server model for communications. A server is an application that offers a service to internet users. A client is a requester of a service. An application consists of both a server and a client part, which can run on the same or on different systems. Users invoke the client part of the application, which builds a request for a particular service and sends it to the server part of the application using TCP/IP as a transport medium. The server is a program that receives a request, performs the required service, and sends back the results in a reply. Introduction to congestion control. In this video, we are going to see about introduction to congestion control. When large amount of data is fed to system which is not capable of handling it, congestion occurs. TCP controls congestion by means of window mechanism. TCP sets a window size telling the other end how much data segment to send. TCP may use 4 algorithms for congestion control. Additive increase, multiplicative decrease, slow start, fast retransmit, fast recovery. Additive increase, multiplicative decrease. In this video, we are going to see about additive increase, multiplicative decrease. Additive increase. The exponential growth of window size has to be reduced as the threshold level is attained. The additive increase strategy continues till the window size reaches the window size of receiver so as to avoid congestion. Multiple decrease. At the time of congestion in a network, the probability of segment lost will be higher than the segment getting corrupted. Hence, when a timeout occurs, the threshold level has to be reduced to half the value of previous congestion window size and a new start should take place. Size of threshold has to be reduced for each and every timeouts. Hence, the threshold size reduces exponentially, which is called as multiplicative decrease. The procedure is a better method to avoid congestion in a network. Slow start. In this video, we are going to see about slow start. Slow start. A requirement for TCP software implementation is a mechanism used by the sender to control the transmission rate, otherwise known as sender-based flow control. This is accomplished through the return rate of acknowledgements from the receiver. At initial state, TCP sets congestion window size to maximum possible segment size. The increase in window size is continued till the threshold, that is, half the level of window size allowable level is reached. It is known as slow start, and it is not an efficient method since it misleads the processes which are not at all slow. Fast retransmit. In this video, we are going to see about fast retransmit. When a duplicate acknowledgement is received, the sender does not know if it is because a TCP segment was lost or simply that a segment was delayed and received out of order at the receiver. If, however, more than 2 duplicate acknowledgements are received by the sender, it is a strong indication that at least one segment has been lost. The TCP sender will assume enough time has elapsed for all segments to be properly reordered by the fact that the receiver had enough time to send 3 duplicate acknowledgements. When 3 or more duplicate acknowledgements are received, the sender does not wait for a retransmission timer to expire before retransmitting the segment as indicated by the position of the duplicate acknowledgement in the byte stream. This process is called the fast retransmit algorithm. Fast recovery. In this video, we are going to see about fast recovery. Fast recovery. Since a fast retransmit algorithm is used when duplicate acknowledgements are being received, the TCP sender has implicit knowledge that there is data still flowing to the receiver. Rather than start at a window of one segment as in slow start mode, the sender resumes transmission with a larger window, incrementing as if in congestion avoidance mode. This allows for higher throughput under the condition of only moderate congestion. Notice the periods of exponential window size increase, linear increase, and drop off. Each of these scenarios depicts the sender's response to implicit or explicit signals it receives about network conditions.